The core part of the talk is going to be focused on the use of shortcuts to adiabaticity to essentially be able to get machines which work with high power and high efficiency. And there are some very nice experimental results unpublished, which I will present there. I will discuss as well what's the cost of doing shortcuts. Yeah? If they are so nice, well, maybe they come at some cost, and we will see it's very small or almost no cost at all. And the last part is counterintuitive result that comes from the true energy projective measurement definition of work, which was already discussed by many of you. So let's get started. So we know that quantum thermodynamics has been either motivated by the development of technology. Now we have an experiment with a single ion heat engine. So we are really at the nanoscale entering the quantum regime. We also have nice experience from Tecolab with other kind of systems. And the other is, just from a purely theoretical point of view. So there are questions which call for the formalization of these ideas in quantum thermodynamics. The talk is going to be exclusively focused on quantum heat engines, and it's very nice to have in the first row the persons who suggested that it was actually a good thing to play with. And as a kickoff motivation, I'm going to use this relation which has been established between quantum heat engines and light harvesting either in artificial or natural systems. Yeah? So this was work by Marlan Scully, Mukamel, Dorfman, and Voronin, and later as well by Susana Huelga, Martin Peña, and colleagues. So very naive expectation is that maybe you learn how to engineer quantum thermal machines which are very highly efficient. Maybe you are able to transfer that knowledge to artificial systems. So here is the scheme. So actually, I'm going to be focused pretty exclusively on the Otto cycle. And there's a very nice review about it, which was published this year, and experiment which got pretty close to the realization of the Otto cycle by actually one of the organizers, Ferdinand Smith-Callus group. And the idea is there will be 4 strokes, one in which the working substance expands, doing some work, then it's cooled down, then it can be compressed, and then it can be heated up to return to the initial state, and the cycle goes on periodically. And when you have such a cycle, you can actually just realize that 2 of the strokes are governed by unitary dynamics, so the system is isolated and decoupled from heat baths, and then it's fair to define the work as the difference between the energy of the final state and the initial state. And with that information, you can compute the efficiency and the power, yes, which are the typical ways to characterize the performance of a heat engine. Good. So the focus on this first part of the talk is going to be on trying to identify many particle effects which could boost the performance of a heat engine. In the quantum domain, of course. So the comparison I want to make is, imagine I perhaps talk to Ferdinand and he tells me, I have few ions, what can I do with them? Shall I create a thermal machine where all the ions, maybe an ion chain acts as a working substance, or perhaps is it better to use, lots of small engines in parallel, which are, it's just an ensemble of independent heat engines. I'm not going, the other question is perhaps it's better to do it with cold atoms instead of ions, maybe NV centers. So, what kind of working substance should we consider? Yes. So, in the, if I focus on particles which are confined in a harmonic trap, this is the picture I have in mind. So I plot the mean energy with respect to the frequency of the trap, and I can drive the engine between a highly a kind of high temperature equilibrium state, decompress it, and then cool it down, compress it, and heat it up again. So this is the many particle variant of the Otto cycle. And as a working substance, I'm going to consider particles which are identical with the same mass. They are all in the same trap, and they interact with each other through some pairwise interaction potential. And I'm going to focus on a kind of interaction potentials which is a scale invariant, so it's a homogeneous function of degree -2. So if I multiply coordinates by a given constant gamma, I can pull out that constant with a factor of -2. And why this case? Well, it's suggested in this picture. If I look at the density profile at different times, then it will preserve the shape, and it will only change by a scale, so the width of the cloud is changing, but other than that, the shape of the cloud is unchanged. So it's only under these kind of interactions you recover the same kind of dynamics that you have for the single particle harmonic oscillator. So everything is scale invariant, and I'm just going to look at these kind of transformations.
So, Doctor,
Yes.
Is this the scale invariant
Sorry.
Anatoly calculated for 1D systems?
So this is the scale invariant that you have in a two-dimensional Bose-Einstein condensate, that you have it in the Tonks regime in one dimension, so it's fairly, also you have, so yeah, mainly is the in the context of ultra-cold atoms, you will call it Pitaevsky-Ross symmetry, so, these ones, Maxime was working on them to study breakdown of these scale invariants, yes? But all what it means, so in, so in what? In a one-dimensional cloud, if you are thinking of a linear gas with contact interactions, you don't have the symmetry exactly. You can have it exactly at a strong coupling with the interaction when you enter the Tonks regime, or in the non-interacting regime. For intermediate interactions, it will be approximate, which will not kill what I'm gonna say, because the experience you did so that actually you can survive. But exactly the theory demands this property. Yeah? Why is then interesting? Well, the point is that if you have a scale invariance, then you can work out the finite-time thermodynamics exactly and essentially for free. In particular, you can compute the non-adiabatic mean energy at any time in terms of its initial value and the initial value of the squeezing and the particle fluctuations. So this is very nice because it's, this is a relatively very generic, fairly complex system. It can be in any dimensions, and then, however, I claim that we can find exactly with no approximations the evolution of the mean energy in terms of this very simple equation, where all the coefficients are just governed by this equation, which is actually classical. It's a second-order differential equation where the scaling factor, essentially, this is the size of the cloud, the width of the cloud, depends on the frequency of the trap. And given a modulation of the trapping frequency, you can learn how the width of the cloud is changing. Now, another thing which is very nice is that I can compute the ratio between the non-adiabatic energy and its adiabatic value. And this coefficient is known to play a key role in quantum thermodynamics of heat engines. And I'm going to, typically it's known as the non-adiabatic factor, but essentially it captures quantum friction, yes? So if there's a non-adiabatic excitation, this coefficient is larger than 1. In the adiabatic limit is obviously equal to 1. And one can find a close expression for it in terms of the scaling factor, the width of the cloud, and the modulation of the trapping frequency. Yes?
In this case, the noninteracting excitations are kind of not incoherent in the sense that you probably follow a ground state of some other Hamiltonian. So it's excitations only with respect to this Hamiltonian, but you sort of don't generate entanglement or whatever. You
generate a squeezing, yes, during the dynamics, if you want, and you produce, so you are exciting the breathing mode because you have, and maybe you could effectively, there's an invariant of motion which you can picture as a Hamiltonian, and this is something that, together with Chris Jasinski, we clarified in 2014. So the invariant of motion is kind of an energy invariant of motion and looks like a many-body Hamiltonian. But it's not it's a strange one. It will have a magnetic field and things like this. Well, as an example, and this is just a brief example, I can take a one-dimensional cloud of particles which interact with this kind of interaction, which might look a bit strange. But it's good because it allows me to keep track of ideal non-interacting bosons and hardcore bosons just by changing the value of lambda. And it has many other properties. It's known to be an ideal gas of particles which obey fractional exclusion statistics. And in particular, what I like it is that essentially the only effect of the interactions is to shift 0 point energy fluctuations. So it's is an integrable system which is very pathological in some sense, where the excitations are those of a free Bose gas, of a free Fermi gas, but the only effect of the interactions is to increase the 0-point fluctuations. So that will give you some idea of what's going to be the effect, because the gas will be more incompressed. It will be harder to compress the gas at large lambda. Yeah.
Adolfo,
Yep.
Can these be non-contact interactions?
Well, here I'm explicitly writing this. Actually, it's a power law, so this is the Caloyero-Sutherland gas. It hasn't been done in the lab yet, but it has two limits which are well realized in the laboratory, which are hardcore bosons and non-interacting bosons. Yes. So for these two cases are contact interactions. For any other finite value of lambda, is a power law. So.
And you can.
And everything is solvable. It's one of these famous models in mathematical physics named Caloyero-Sutherland model, where you can find eigenstates, eigenvalues, and so on. Good. So for this system, it's just to give an example. We can keep track of all the. We can compute everything exactly with no approximations, and we can then look at the efficiency and the efficiency in finite time. So when I write the thermal machine in a non-adiabatic way, and what I can find first is this bound, where the non-adiabatic efficiency is always upper bounded by this expression, which looks like the Otto efficiency up to this non-adiabatic factor, which is the non-adiabatic factor in the expansion stroke. Yep. So that's kind of a nice bound to understand the non-adiabatic efficiency of this machine. Now I can look at the comparison between this setup, where I take a heat engine with many particles and an ensemble of few particle heat engines, and I can define the ratio of the efficiency of the large machine with respect to the efficiency of one of these smaller machines. And I can also define the ratio of the power, so I look at the power of the large machine and n times the power of one of these heat engines.
So what do you use as a mechanism to couple to the back and decouple to the
Oh, so this is the part that in this Otto scheme I am actually not focusing on the coupling to the bath. What I'm assuming is that once I compress the system, I couple it to a bath and it reaches thermal equilibrium by some means, and I am not specifying it. I am just assuming that this is the case. In the context of colatons, perhaps you could think of bringing a cloud and just use sympathetic cooling, but it will be a difficult experiment to do with colatons. But you could envision doing something like this. With ions, maybe it's easier, at least certainly the heating, then the cooling maybe as well. So I just want to look at the ratio of the efficiency between this setup and this setup, and the ratio of the power, yes? And what I'm going to define as a quantum enhancement is the scenario where both the ratio of the efficiency and the ratio of power gets larger than 1. So if I increase the efficiency and I increase the power just by using this many particle setup, I will claim that I have a quantum supremacy. And I can claim that the effect is purely quantum. I can solve it. And well, you can do the simulation, and this is what you find. Effectively, you can look at the ratio of the efficiency under sudden quench driving, so when I drive the system very fast, and I can show that it's always larger than 1. So it turns out that it pays off, you can increase the ratio of the efficiency just by increasing the number of particles when you use this configuration over this scenario where I have an ensemble of single particle heat engines. The same thing happens for the ratio of the power. The enhancement is not so spectacular, it's just about a 10%, and actually it's not monotonic, eventually it can get worse, yes? So, but for these parameters, I saw that the ratio of efficiency and the ratio of power is larger than 1, so I'm getting, essentially enhancing the performance of the heat engine as much as I can, yes? Only by using many particle effects. The effect of the interactions is actually to diminish the enhancement, so it pays off to have non-interacting particles. At least this is, for this specific model, I cannot claim that this carries over trapped ions, for instance, because this is a strictly one-dimensional many-body system, and it might be that in trapped ions, for instance, the physics is just different. But for this system, ideal Bose gas is very good, so I have this supremacy, but if I look at hardcore bosons, then the performance gets worse. So it does not pay off to engineer a many-particle thermal machine. It's actually better to use single-particle thermal machines so that the ratio does not get smaller than 1. Right, so this is a quick summary here. We have shown that, in principle, we have quantum supremacy just by engineering many-particle thermal machines in a non-adiabatic setting. In the adiabatic setting, there is no supremacy. All the ratios become equal to 1, and it doesn't make any difference whether you are using a many-particle setting or an ensemble of single-particle heat engines. Yes? Good. Yeah, and of course, one can think that perhaps it would be lovely to be able to transfer this to some other setup, but this is far-fetched at the moment. Yeah. Yes.
I'm going to say why it's quantum, because when the number of particles is large, it's extremely hard to.
Yeah, so I can, what we saw rigorously is that in the non-interacting case, well, we can do the comparison of the classical gas and the interacting gas, and then we find that it's a quantum effect. Then we also have analytical expressions where all the improvements above the classical result are quantum. I'm not displaying them here, but I have actually a couple of slides at the end. Maybe if there is time. I'm going now to move to a second part where I'm going to tailor non-adiabatic effects. So the idea here is to be able to create a quantum heat engine, which I run very, very fast, and still I run it at high efficiency, in particular at maximum efficiency. And to do that, I will use these techniques that were already presented by Anatoly Polkovnikov on shortcuts to adiabaticity. So the setup is the same. I'm considering a many-particle quantum heat engine. And the point now is that instead of doing this expansion and compression in a standard way, I'm going to try to control excitations such that I set friction to 0. I have no friction. And then the efficiency will be maximum. We have already seen that generally in finite time, the efficiency is limited by this upper bound, and this is kind of motivated by Ronnie Kozlov's way of putting it. If you want to play James Bond and have a fancy car, then you might not be very eco-friendly. Yeah? So we have this trade-off between power and efficiency, and this has guided the design and optimization of quantum heat engines for many decades. And what I'm going to claim is that this trade-off is not fundamental and actually can be avoided using shortcuts to adiabaticity. So what are the shortcuts? Well, so these are non-adiabatic processes that reproduce or mimic adiabatic dynamics, say in the preparation of a given state. And I'm going to focus on expansions and compressions, but these ideas have been formulated in a fairly general setting to do splitting and phase transitions, swapping, even quantum logic, at least in some cases, and also implemented in a variety of systems. Yes. Let me skip this. So the idea is to just use shortcuts to avoid this trade-off between power and efficiency, and this builds on some work that I did together with John Gould and Mauro Paternostro in 2014, and later on, essentially at the same time, the group of Jan Bingon in Singapore, together with Peter Hangi, proposed the realization of the single particle level. Both of these works are essentially focused on single particles, and then a year ago we extended to the many particle setting. So what's the idea is essentially just to substitute this expansion and the compression stroke by superadiabatic variants, where we do a shortcut to adiabaticity. So the question is, according to the adiabatic theorem, the only way to suppress, or the natural way to suppress excitations during expansion, if you start in an equilibrium state and you want to end up in an equilibrium state, is to go slowly. And the point is that there are non-adiabatic modulations of the frequency of the trap that also will allow to reach an equilibrium state in a finite time, in a small time.
When you say equilibrium, do you mean thermal equilibrium or do you mean einstate?
I mean that is well. So in in that case, typically in the more general setting, I have a notion of adiabatic continuation, and I just mean that I'm following the adiabatic manifold without inducing any transitions to other states. At least the final state will be the same. Yeah.
And also, well, we prove that the scale invariant potentials they equivalent.
Exactly. So for ones would, yeah. As Chris knows, but with the scale invariance, you can understand it in different ways, I would say. So, but this is what I'm going to do. I'm still going to focus on scale invariant dynamics of a harmonically trapped system, and where I change the frequency of the trap to drive a expansion or a compression. And the point is that the final state should be free of excitations, and such that the quantum friction is 0. How can I do it for this system? Well, the theory of shortcuts can be used in combination with the scale invariance to get a very simple protocol where for any, you picture a given trajectory that you are interested in, say lowercase omega of t, and you run it in finite time, and typically you will have excitations. So the idea is if you correct that trajectory with gradients of the frequency and the acceleration of the frequency, so to speak, then this modulation will suppress excitations upon completion of the protocol. And the best is to just show you the experiments that Georg Schmidmayer did a few years back, where he compared the linear decompression of a one-dimensional Bose gas. So this is a system where actually you don't have exact scale invariance, but still the theory applies as an approximation. And when you do the experiment, it turns out that it is just pretty wonderful. Yeah? Essentially, you can do the shortcut. So you compare the linear expansion in some time scale, here around about 30 milliseconds. And if you picture the radius of the cloud, you can image it, and then you see that you have induced huge breathing excitations of the breathing mode. Now, you can use the theory of shortcuts to design an alternative protocol where you do a fast expansion, then you compress the cloud a bit, and then you expand again. And what you see is that through this non-intuitive modulation of the frequency of the trap, the cloud expands until reaching the equilibrium state of the final trap, and up to noise essentially stays there. Yeah? So in the same time scale, through this modulation of the frequency in red, you are able to suppress excitations and have no friction. Yes? So the theory went through a series of stages where it started at the single particle and extended to many particles, and then in a fairly general way, again together with Chris Jasinski and Sebastian Döpfner, since we formulated. And the experiments started very early on. First at single particle thermal clouds, so no interactions. Then mean field Bose-Einstein condensates, and then one-dimensional Bose gases with phase fluctuations which go beyond mean field. Yeah? And what I want to show now, so these are essentially unpublished results, is whether you can use it in a strongly interacting system, which you will have a hard time to describe by any other means. It's at a strong coupling, and this is the so-called. The example is the Fermi gas at unitarity. So the system. We'll hope to submit it pretty soon, maybe this week or next week. So this is work with Haibin Bu and it's East China Normal University, and with Aurelia Senu, Ivan Kolami, and essentially it's Haibin's group at the ECNU. So the system is, is still a bunch of particles in a harmonic trap. It's a spin 1/2 system, so you have a spin up and down component, and now the interactions are only between a spin up and a spin down. Now, for any finite coupling strength, you do not have a scale invariance, but you can recover scale invariance at strong coupling when this constant is very, very large. And there, essentially, conformal symmetry appears as an emergent symmetry exclusively at the strong coupling. You recover this property, which is going to allow us to do shortcuts to adiabaticity in this system. How it looks in the lab? Well, it's we heard from Georg Schmidmayer yesterday that with cold atoms it's good to take pictures. So this is what you can do. You can image the cloud, which this I took with my cell phone. It's just a unitary Fermi cloud over there, which is fluorescing. And of course, then there's a whole bunch of optics to control the system. And we can, again, solve both. We can tune the interactions from the non-interacting case to strong coupling. And in both cases, we can show that we can engineer shortcuts to adiabaticity where the cloud expands and essentially stays at equilibrium in a time scale in which typically we will expect to create breathing excitations. Yeah? So it's the same physics, but now it's implemented in a strongly coupled quantum fluid, which is actually very difficult to describe, and where you do not have access to spectral properties, so you cannot use the standard techniques of shortcuts to adiabaticity, and you can only do it thanks to the scaling variance, essentially. Now, the wonderful thing is that in this system we can also extract the quantum friction, and we can see two trajectories. One in which I just do an expansion of the cloud, so at different stages, and I can monitor quantum friction, and then you see that it is growing and growing, and at some point you end up the experiment. If you use a shortcut to adiabaticity, what you see is along the process you create huge amount of excitations. But what you care about for the quantum thermodynamics is what's the value of the quantum friction upon completion of the stroke, at the end of the expansion. And there you see that it comes back to unity. Yes? So you are able to suppress quantum friction, the unitary Fermi gas, which is a quantum fluid at strong coupling, by using shortcuts to adiabaticity. Yeah.
How does it continue? Then it stops? I mean.
Oh, well, this is at equilibrium state. So, I mean, we are not monitoring it, but this is an equilibrium state. So, it just starts with, end up with the mean energy of the corresponding value if you have driven the system slowly, adiabatically. The other one, just has this excess of energy. Yeah. The dynamics is unitary, so mean energy is conserved if you stop the Hamiltonian. We can then, the idea is to use this in the expansion and in the compression, and with that, yes?
Actually, for a heat engine, what you care is not getting to the same population. You care of reducing the energy without changing the energy. So there are situations where...
In the quantum Otto cycle, we'll have the explicit expression of the efficiency, and it's governed by this factor. And all what I'm showing is that if I am able to set it equal to unity, then I'm reaching the maximum efficiency. Yeah? I'm focusing on the unitary strokes, where the system is decoupled from an environment, and the dynamics is...
It's not totally general. There are situations that you want to reduce it, but we can discuss it.
Fair. I mean, this is as good as we can do at this stage, yes. So the idea is to replace these expansion and compression strokes by these superadiabatic variants, and by doing so, we are able to, essentially set the efficiency of the engine in finite time equal to its maximum value. Yes. So we are able, essentially, you can think of it as a quantum control approach, but it's generic, and I can engineer it for any time tau. I can find a shortcut, no matter how small this time it is. I can find a shortcut in which I get the maximum efficiency. And excess of work along the process also increases, but then it does vanish. Yes. But the point is, I get maximum efficiency in any arbitrary operation time. This is without taking into account the heating and cooling strokes. So the conclusion here is that STA can be applied not only in weakly interacting systems, but also at a strong coupling, and that the scaling variance is the key to get results in this regime, because otherwise it will be impossible. Computationally is untractable, and we are able to control the finite-time thermodynamics to engineer processes which go very fast and yet have no friction. Yes, so this is the key. Now, I can move to quantify now get a bit far away from the experiments and try to understand more generally what's the cost of doing shortcuts. And in order to do it, I'm going to move to a universal way of engineering shortcuts, which is a bit different from the one I have presented so far, based on modulations of the trapping frequency. And possibly this relates to Anatoly's talk. Yeah. So the idea is, this beautiful trick of so-called counterdiabatic driving, that whenever you pick your favorite Hamiltonian, H0, so think of a trapped ion, an NV center, whatever you want, and you change some parameters, then you assume you have access to the eigenstates and the eigenvalues. Of course, if you are changing the parameters slowly, then you can write down the adiabatic approximation, and it picks up the dynamical phase and the geometric phase, and then you follow the instantaneous eigenstates. Now, you might wonder whether I can enforce this adiabatic approximation to H0 as an exact solution, not an approximation, but an exact solution for a different Hamiltonian that hopefully will be related to your system of interest. And the answer is, yeah, you can always do it. You can always find this Hamiltonian for which the adiabatic approximation to H0 becomes the exact solution of the time-dependent Schrödinger equation, and you can write it as your system of interest plus some auxiliary control field that is the counterdiabatic control field. So this is the term that cancels excitations as you are driving the system. And generally, to engineer it, you find if you have access to the spectral properties, you can find this control. In the experiments on unitary Fermi gas, we avoided the requirement of spectral properties by using scale invariance. But in a more general setting, you will need to know what are the eigenstates. So this idea is not mine. It was actually introduced by Stuart Rice and his postdoc, Mustafa Demirtak, and rediscovered by Michael Berry independently along the derivation I have presented. You can also rewrite, almost generally, the control term that is required to suppress excitation in this form, which resembles adiabatic perturbation theory, because you have the rate of change of your system, Hamiltonian, and over the gaps, and then you have non-local matrix elements between different energy eigenstates. And from there, you can get an idea of how complex this control can be in the general setting, because it's going to couple any eigenstate with any other eigenstate. So it's possibly a kind of a monster. For simple systems, there were a couple of experiments last year demonstrating the realization of counterdiabatic driving. It's not the only way of doing shortcuts, but for 2- and 3-level systems, this was implemented in an optical setting, and together with P1 Kim at Tsinghua University and experiment by Sominan, we were able to do it for a single trapped ion in phase space. Now, of course, the experiments are always more complex, which is something good to remember from time to time. And what I want to focus is a bit on the cost of this term, in particular from the thermodynamic point of view. So one thing we can show is that the mean work along the shortcut equals to the adiabatic work. So essentially, the mean work done by this term is strictly 0. Yeah? I'm not doing any work, thermodynamic, quantum work, by implementing this term. However, I'm actually changing the work statistics, so I can look at the variance of the work distribution in the presence of a shortcut and compare it with the adiabatic driving. Yeah. So I am essentially, when I do a shortcut, I essentially increase the variance of the work fluctuations. And it turns out that the difference is given by this beautiful expression, which is kind of a thermal mean. So these are the occupation numbers and the energy basis of my initial density matrix. And here I have the quantum geometric tensor for each of the eigenstates. Yeah? So the quantum geometric tensor was introduced by Provost and Valle, and essentially tells you how eigenstates are changing as I drive the system. And it provides a metric in Hilbert space, which is the Fubini-Static metric. So what is interesting is that the excess of work fluctuations due to the shortcut are precisely given by this kind of thermal average of the quantum geometric tensor for each eigenstate.
Adolfo, can
Yeah.
you explain this? Maybe I'm missing something. But if you're doing the shortcut, in the end you go from one eigenstate to the other. So in each realization you get the same amount of work with the same probability as if you do adiabatically. No?
Yeah.
So
thank you. I actually, So I thank you for this, because actually for all what you care about in the experiments is whether upon completion of the stroke you have the same work statistics or not. And with shortcuts you do have exactly the same work statistics. What I'm doing is actually, maybe I'm complicating things a bit. I am stopping at any point of the shortcut and asking how much work I'm doing. But actually, if I finish, it's perfect adiabatic state.
Like what you
So,
need
yeah.
to go along the...
Yeah, it's just only to quantify the resources that I need along the process. But actually, if you only, for the performance of a heat machine, you only care about the endpoints, and then it's perfect adiabatic matching. Yeah? But thanks for that point to clarify this.
Yeah, I just want to comment. So you get exactly identical expression without counterdiabatic, but not if you are sufficiently slow. Kind of interesting.
You mean in kind of linear response or?
Identical expression, for variance with this metric terms and so on.
Well,
This leading non-adiabatic.
which is very nice, and I think it makes sense because, because
Something about this.
shortcuts enforce adiabatic following even when you go fast, and it is very interesting.
It
Yeah.
remains the same, but now it's not just in the slow lead, it's all
Yeah. Very good. So we actually should talk more about it because I'm not sure I really know the works you are referring to. But this is the first time we found this kind of thing. Maybe it has appeared in other settings. With it, what we can do is, from the quantum information point of view, this thermal mean of quantum geometric tensors is a strange object. And given two density matrices, you always prefer to use the Bose angle, which is the arc cosine of the square root of the fidelity. So one thing we can show is that, well, the metric that is suggested by counterdiabatic driving is, well, first of all, it's actually a metric, and for it we can derive an exact work time certainty relation. So I know, given a time of the process, I know what is the excess of work fluctuation. So if I want to go faster, I need to increase work fluctuations along the process, so this is kind of a speed limit, but now formulated for rather than time and energy, is time and work fluctuations. Now I can lower bound this distance by the Bose length, which is maybe more familiar to you, and then I can write. I lost the quality here. I get an inequality, but I can find this is very similar to a time energy uncertainty relation. I find that the time of the process is constrained by the distance between the initial and the final state, and the notion of speed of evolution in Hilbert space is given here by the excess of the variance of the work fluctuations. Yes, it's a strange thing, which I wonder how general this is. This bound turns out to be better than the usual bound, which is the one you can find in textbooks. So you take Messiah and you read about time, energy, and certainty relation, you will find this result. So the time for a process to happen depends on the energy fluctuations. And if you increase energy fluctuations, you can go faster. So, but the strange thing is that here we are able to find a time work uncertainty relation it is actually tighter than the usual time energy uncertainty relation. So I'm not actually, this is something we would like to understand how general this is.
Why? How can it be?
I would say I don't have a very close intuition about it.
Isn't there a contradiction somehow? Time, energy, uncertainty cannot be violent.
Yeah, so I'm not violating anything, I'm just finding a better bound. It's known that for general dynamics this bound is not tight, so this bound can be reached for very specific processes, but typically this is so-called Mandelstam time energy uncertainty relation, and it's generally not saturated, yes? In particular for time-dependent processes, typically is a bit far off the real time for things to happen, yes?
Basically you are saying that the real time uncertainty relation is tighter than what you might think, no?
No. Yeah, I would say just the contrary. For time-dependent processes, in particular for shortcuts to adiabaticity, maybe this result is not so tight as others that you can find, for instance, by bounding the speed of evolution in terms of the excess of work fluctuations. Yeah. We can discuss it further. I mean, if I look at this, we have also looked at this in some other contexts under shortcuts. I'm glad it excites some discussion. You have a question? Wrap up? How much minutes? Over? Yeah? Okay, so maybe I can just close here. Then, yeah? Or I have a couple of minutes.
Just conclude.
Okay. Well, so I
take a lot of discussion.
Very good. So I just conclude this a pity I couldn't tell you about the last part where we realized that the efficiency of a Feldman machine when characterized for a single cycle does not carry over many cycles when you are doing work on a quantum system. So this is just work together with, maybe I can just mention it, together with Gentaro Watanabe, Benakates, Peter Tockner, and was also reported this year. But let me just skip it. I want to advertise also that we are editing a focus issue on shortcuts to adiabaticity, so it's currently open for submissions. And I just want to thank the collaborators at UMass Boston, the current group, previous members who were involved in the first part of the talk, and a bunch of collaborators all over the place. So thank you all for your attention. Yeah.
Well, thank you very much for your very good talk, and was a very good discussion. I like this. So, Eric?
I'm slightly confused by the claim that you can reach maximum efficiency at finite power, because there's this recent PRL by Saito and co-workers showing that this is not possible in general. So I would argue that we might have to change the definition of the efficiency to include the particle shortcut, as we did recently. But this is an open discussion, right?
Yeah.
Yeah, please, let me know.
The prefactor that they have, it's a very nice result that they obtain, but the prefactor is not universal, and this means that you can find ways to actually violate the bound that they obtain.
Talking about Adolfo's paper or Saito's paper?
Saito's paper. So it's
fluctuations in power.
No, it's not related to fluctuations of power. But we actually wrote a paper where we showed that we can actually get arbitrary flows to down in finite time, and we showed that the reason why the cycle doesn't work is because the prefactor actually goes to zero.
So maybe just a quick comment. Yeah. So we have been, other than the use of shortcuts, I think we have been very traditional, and in the current way of quantifying the efficiency of an Otto cycle, you never quantify what's the protocol. You are agreed that for any protocol, you have some energy consumption and some work output, and we have just find specific protocols for which quantum friction vanishes. Yes. So in particular, I don't see this. This is a very general way of doing that, but it's not that different from, for instance, the accidental shortcuts that Ronnie Kozlov found, in this harmonic oscillator. Yes. I think it's perfectly. I don't see anything really provocative. I mean, once you realize that such protocols exist, it's just whether for unitary processes, work is just the difference between the energy of the final and the initial state, and you don't care about how you have got there, as long as you have done it in a unitary way, driven by a Hamiltonian. Yes. If we start to quantify the cost of the Hamiltonian, this is what I try to do in the part of work time uncertainty relations. But no one ever has questioned, from a thermodynamic point of view, what's the cost of implementing a thermodynamic, a unitary protocol.
First, there was the question.
Did you try to estimate by how much quantum anomalies can help your shortcut? Because 2D gases are much more accessible than
in a perturbative way, I would say, yes, because the experiments by Georg Smith-Mayer show that even if you don't have exact scale invariance and your expansion factors are moderate, a factor of 4 or so, then shortcuts work perfectly. Yeah.
So many questions. I think you were first, and then
I just want to make a comment. So you had very nice expression for the time balance, but I just want to comment that if you engineer the ergodic system by this eigenstate minimization hypothesis, you get exponential only time, because this metric, except for the ground state, it's actually exponentially big. So exactly, which kind of makes sense if you want to follow really adiabatically. Exactly.
Which does not. You are just saying that if I evaluate explicitly the expressions I have found, then they have a dependence which is fine. Yeah. With this, which is encoded here, and we have characterized it actually for critical systems, for instance.
I think this unitary stage is a problem. It's always a kind of approximation, which never appears really in real systems. So to have it as a good approximation, you need what you said already. You need to take into account the cost of switching on and switching off the interaction. Moreover, I do not believe that you can have, from very basic principle, the equal work for different trajectories of this potential, because work and heat depend on the trajectory. So it's simply impossible that such drastic change of trajectory can produce the same work.
So I guess I can answer. Yeah. So the first part was about putting in contact and removing the contact with the heat reservoirs. I fully agree with that criticism. Is generic to all studies on the quantum on the Otto cycle. Yes, there's nothing specific about this work. So we agree that we have to take it into account, and I'm very keen on doing that. We will get different results, but I don't think that challenges the results I have shown here. Yes, because I have essentially shown that with respect to the standard way of doing it, we can just do much better by doing shortcuts. And then for the second part of the question, well, I would say that for unitary protocols, your point does not apply. If I have coupling to above, I agree. But if I assume that during the expansion and compression strokes, I am perfectly isolated, decoupled from the bar, then I would say...
So basically you're saying both lead to the same question, switching on and off.
This is an interesting question. Yes, yes. But again, generic to all Otto cycles. I mean, there's nothing specific from these studies.
No, Fred. Yes, yes. You said that you made this discussion about quantum supremacy and what happens if I have plenty particles next to each other or all in one trap or something. And like having them all together is better. Do you have some physical insight why this would be?
Yeah.
On what does it depend?
So I don't have a very rigorous proof, but essentially is so this is something I was discussing with Gerson at some point. So when we get the maximum enhancement is for a Bose gas, non-interacting Bose gas, where essentially I have lots of degenerate states and symmetrized excitations essentially. The gas is also maximum. So the compressibility of the gas is the maximum. But on top of that, I have a high degeneracy. So you can think of maybe how to carry this to other systems. Sorry.